We now start the presentation of module 3 of chapter 4. See that we have already defined two types of convergences. One is convergence almost everywhere and another is convergence in measure in the last two modules. We have seen their basic properties and we have also established the relation between the two concepts by showing that in general none of the concepts imply the other, but we have finished the last module with a result that and on a set of finite Lebesgue measure, if we consider a sequence of measurable functions f n and f, then f n converges to f almost everywhere implies that f n converges to f in measure. So, in a set of finite Lebesgue measure, convergence almost everywhere is stronger than the notion of convergence in measure. Now, what we are going to do in this module is that we will consider a notion which is more general than the notion of uniform convergence, and we will see its relations with the notions of convergence almost everywhere and convergence in measure. So, we start by recalling the definition of uniform convergence. A sequence of real valued functions f n defined on a subset of R is said to converge to a function f uniformly if given epsilon greater than 0, there is a positive integer n which is dependent on only epsilon such that mod f n x minus f x is less than epsilon for all n greater or equal to capital N, and this is true for all x belonging to capital A. Now, we will give another notion of convergence with respect to measure, which is more general than the notion of uniform convergence. A sequence of real valued functions f n is said to converge to a real valued function f almost uniformly if for any delta greater than 0, there exists a measurable set capital F with mu of f less than delta such that f n converges to f uniformly on f complement. And in this case, we write f n converges to f almost uniformly or a u. The first result which we will prove is that if f n converges to f almost uniformly, then f n converges to f almost everywhere, and further if in addition all the functions under consideration f n f are measurable, then also f n converges to f in measure. See, first we start with our assumption that f n converges to f a u, then by the definition for any positive integer m we can find a measurable set f m such that mu of f m is less than 1 by m, and on f m complement f n converges to f uniformly. So, for each positive integer m, we get a measurable set f m, and let us take f as the intersection of all these sets f m, that is intersection m equal to 1 to infinity f m. See that since mu f m is less than 1 by m for all m, so mu f is less or equal to mu f m less than 1 by m for all m, which shows that mu f is equal to 0, and obviously for all x belonging to f complement, f n x converges to f x. And so, we have proved our first assertion that f n converges to f almost everywhere. Now, we go to our second assertion. Let f n and f be all measurable and f n converges to f almost uniformly. Let epsilon greater than 0 be given. Let us write the set x where mod f n x minus f x is greater or equal to epsilon as the set E n. Now, let delta greater than 0 be given arbitrarily small number. Choose a positive integer small m belonging to capital N such that 1 by m is less than delta. Let f m be the set as defined before, that is f m is a measurable set whose measure is less than 1 by m, and on f m complement f n converges to f uniformly. Now, from the definition of uniform convergence, we can find a n 0 belonging to capital N such that mod f n x minus f x is less than epsilon for all n greater or equal to n 0, and this is true for all x belonging to f m complement. But then f m complement intersection E n must be equal to phi for all n greater or equal to n 0. Why? Because E n is the set where mod f n x minus f x is greater or equal to epsilon, and on f m complement for all n greater or equal to n 0, mod f n x minus f x is less than epsilon. This implies that E n should be a subset of f m for all n greater or equal to n 0, and consequently mu of E n is less than mu of f m, which is less than delta, and this is true for all n greater or equal to n 0. So, we have the sequence mu E n satisfying the criteria that for any delta greater than 0, we have found positive integer n 0 such that for all n greater or equal to n 0, mu E n is less than delta, and this means that limit n mu E n is equal to 0, and so f n converges to f in measure. Next, we are going to prove a very important theorem in measure theory, which is named as Egoroff's theorem. The Egoroff's theorem states that if Fn, n belonging to capital N, is a sequence of real valued measurable functions defined on a measurable set A of finite Lebesgue measure, and if Fn converges to F almost everywhere on A, where F is also measurable, then Fn converges to F almost uniformly. So, in other words, when we consider a set of finite Lebesgue measure and consider the three types of convergence of sequences of real valued functions defined on those sets, convergence almost everywhere is the strongest form of convergence, and it is actually equivalent to convergence almost uniformly. We first start with a more stronger assumption that Fn converges to F everywhere on the set A. Now, for each positive integer mn belonging to capital N, let us define a set capital F m n as the collection of all x where mod f k x minus f x is greater or equal to 1 by m for some k greater or equal to n. Now, see that we can write this set as countable union k equal to n to infinity collection of all x where mod f k x minus f x is greater or equal to 1 by m. Now, since by our assumption all the functions f n and f are measurable, so in particular f k minus f is also measurable, and from the definition of measurable function we have that the set collection of all x where mod f k x minus f x is greater or equal to 1 by m, this set is also measurable. So, each set on the right hand side is measurable, and consequently their countable union is also measurable. Also note that the sequence of sets f m n is a decreasing sequence of measurable sets. Now, we will show that the intersection of all these sets f m n is actually equal to phi. Why? Because if we take a point x from the set, remember that by our assumption f n x converges to f x. So, taking epsilon is equal to 1 by m, I have a positive integer r such that mod f k x minus f x less than 1 by m for all k greater or equal to r. And this means that this point x cannot belong to the set capital F m r, and this is true for any point x belonging to the set A, and this shows that the intersection of all the sets f m n is equal to phi. Again, see that as by our assumption mu a is finite, so each of the sets f m n also has finite measure. and using the fact that Lebesgue measure is continuous from above, we have this assertion that limit n mu of f m n, this is equal to mu of intersection n f m n, and this is equal to mu of phi, which is equal to 0. So, the sequence mu f m n is a sequence of positive numbers which is convergent to 0 as n tends to infinity, and this is true for any positive integer m belonging to n. So, given delta greater than 0, we can find a positive integer n m belonging to capital N such that mu of f m n m is less than delta by 2 to the power m. Now, see that for each positive integer m, we get such a set. So, for say m is equal to 1, I have a measurable set f 1 n 1 whose measure is less than delta by 2. For m equal to 2, we have another measurable set f 2 n 2 whose measure is less than delta by 2 square, etc. And now, let us define capital F as the union of all these sets f m n m. Clearly, since each of the sets f m n m is measurable, so capital F is also a measurable set, and moreover mu f is equal to sigma m is equal to 1 to infinity mu f m n m, and this is less or equal to sigma m equal to 1 to infinity delta by 2 to the power m, and the sum of the series on the right hand side is just delta. So, we have obtained a measurable set capital F with measure less than delta, and what is to be shown is that on the complement of this particular set F, f n converges to F uniformly. So, we now show that f n converges to F uniformly on A minus F. Observe that the set A minus F, this is equal to A minus union m equal to 1 to infinity f m n m, and this is equal to intersection m equal to 1 to infinity A minus f m n m by De Morgan's law, and this is equal to intersection m equal to 1 to infinity collection of all x belonging to A, where mod f k x minus f x is greater or equal to 1 by m for some k greater or equal to n m, its complement, but the complement of the set on the right hand side is the set collection of all x belonging to A, where mod f k x minus f x is less than m, and this is true for all k greater or equal to n m. Now, let epsilon greater than 0 be given. We choose a positive integer m such that 1 by m is less than epsilon, and consequently for all x belonging to A minus capital F, we have mod fkx minus fx less than 1 by m, and this is less than epsilon, and this is true for all k greater or equal to nm. And this shows that the sequence fn converges to the function f uniformly on the set a minus f. Finally, let us assume that fn converges to f almost everywhere. Then there exists a measurable set E with mu E equal to 0, such that on the complement of the set E, that is on E complement, fn converges to f. Let us take Gn as the function fn into chi E complement, that is fn into the characteristic function of E complement, and let us take G as the product of the functions f and the characteristic function of E complement. See that this means that on E complement fn is equal to Gn and G is equal to f, and on the complement of E complement, that is on the set E, the values of Gn and G are all equal to 0. So, Gn and G are all measurable functions, as they are products of two measurable functions, and obviously if we now consider the whole set A, at every point of A, Gn converges to G, because the points where we did not have the convergence, we have taken the values of all the concerned functions as 0. So, we can apply the first part of the theorem to the sequence Gn converging to G, and by the first part we can find a measurable set capital G with mu of capital G less than delta. Obviously, Gn tends to G uniformly on the complement of this capital G, that is on A minus G. Let us take the set capital F equal to E union capital G. See that already E has measure 0 and G has measure less than delta. So, mu of f is also less or equal to delta, and on the complement of f, that is on the set A minus f, we have fn which is equal to Gn, which converges to G, but G is equal to f and this convergence is uniform. So, we have fn converging to f uniformly on A minus f, and this proves the theorem. Finally, we will finish this module by showing that the notion of almost uniform convergence is not same as uniform convergence almost everywhere, because if you look at the notion of almost everywhere concept, uniform convergence almost everywhere means that there is a set A of measure 0 such that outside that set the convergence is uniform. Let Rk, k belonging to capital N, be the sequence of rational numbers in closed interval 0 1. Fn is the function which takes the value 1 at the points r1, r2, rn and the value 0 otherwise. So, Fn equal to 0 at all other points of closed 0 1, and this is true for every n belonging to capital N. Now, see that Fn converges to F, where F is the characteristic function of Q, that is chi q on closed interval 0 1. In fact, this convergence is uniform on the set of irrationals, because on the set of irrationals all the functions have value 0, and so the convergence is uniform on a set outside a set of Lebesgue measure 0. So, this shows that I have an example of functions Fn which converges to F uniformly almost everywhere. Now, take the function Gn as the characteristic function of the open interval 0 1 by n for each n belonging to capital N. Then we can again check that this sequence of functions Gn also converges to chi q almost everywhere, and since the domain of definition of all the functions is closed 0 1 and it is a set of finite Lebesgue measure, we can apply Egoroff's theorem, and by Egoroff's theorem this sequence of functions Gn converges to chi q almost uniformly, but there is no set of Lebesgue measure 0 such that Gn converges to chi q uniformly outside that set. So, this shows that convergence almost uniformly and uniform convergence almost everywhere are not the same concepts. So, to summarize, what we did in this module is that we have defined a more general notion than the notion of uniform convergence, namely almost uniform convergence. We have seen that in general almost uniform convergence implies both convergence almost everywhere and convergence in measure when all the functions are measurable. And finally, we have proved a very important theorem, which is Egoroff's theorem, which states that on a set of finite Lebesgue measure, if Fn is a sequence of measurable functions converging to a measurable function f almost everywhere, then it also converges almost uniformly, that is on a set of finite Lebesgue measure, both almost uniform convergence and almost everywhere convergence are same. And with this we finish this module.